All right, so finishing up the last examples from linear models. You have your word problems, your application ones as well. It says a carpenter makes wooden tables and chairs. He makes it takes him 10 hours to make a table and 4 hours to make a chair. The wood costs $120 for a table and $40 for a chair. Find a model for, when it says find a model, it's asking you to find an equation for the time required to make the chairs and B, the cost of making the table and chairs. All right? So when you look at this particular problem, you notice that there are two different variables that we have here, yes? What would they be? I'm hearing a couple of different things. What do we not know in this whole problem? What do we not know? That's true. We do not know the time. We do not know the cost. I mean, it asks us to write a model for both of those situations. So we definitely don't know the time, and we definitely don't know the cost. But what else do we not know? How many tables and how many chairs this carpenter actually makes. So those are actually our variables here. Those are X and Y, or T and C, depends, whatever you want to use. Make sure that you identify what your variables are. And so to write a model, aka write an equation for the time required to make the table and chairs, how long did it take the carpenter to make the table? One table? 10 hours. So if he made 5 tables, it would take him how many hours? 50. And so you can write a general expression to represent the amount of time it took him to create a table as 10T. 10 hours per table. How long did it take him to make the chair? 4 hours. So if you made 4 chairs, how many hours would it take him? 16, because it's 4 hours per table. So you have 4, 4, 4, 4, which makes 16. How would you write an expression to represent how long it would take him to make a chair? It would be 4C. So then the time it would take to make tables and chairs be what operation between? Plus addition. And there's your model for time. Does everybody see how that works? Say it. Not necessarily, because if we look at the time, well, there's 24 hours in a day, so we could kind of try to figure out exactly how many chairs and how many tables he made in one day. But it's not necessarily asking us to do just that. Just write a general expression. What about the cost? How much did it cost to make a table? 120. So if you made 2 tables, that's how much money? 240. A general expression would be what? 120T. How much does it cost to make a chair? $40. So the expression for that would be 40C. To get the cost, the total cost, you have to what? Add them together. Ooh, what does this look like? You've seen this before. Substitution elimination, aka system of equations. Yes, systems of equations are also the applications when it comes to a linear model. Okay? You have to be able to recognize what your variables are, and based off the problem, you have to be able to set up your 2 equations to solve your system either by elimination or by substitution. You guys remember some algebra 1/algebra 2? Okay. So the follow-up question to that says the carpenter in the last example works 70 hours in 1 week and spends $760 on wood. It actually asks you how many tables and chairs can he make. So now we're going to take those 2 expressions that we wrote, the 2 models that we wrote, and this time we're going to do what? Plug in what? We're plugging in the 74 time, and we're plugging in the 760 for the cost. So that was, I think, 10T plus 4C, and 120T plus 40C, I think. And there we go. We have a good old system of equation that we can solve. Which way do you want to solve it? Doesn't matter. We'll get the same solution no matter which way we solve, by elimination or substitution.
Substitution.
I heard like half be elimination. Elimination? Okay. Which variable do you want to eliminate? C. So in order to eliminate C, they have to be the same number, and one has to be a negative in order for them to cancel out. So we're going to multiply the top one by -10, and we multiply the entire equation by -10. So what's -10 times 70?
-7.
And 10 times a -10. So it turns into -100t, and -10 times 4?
-40.
-40c. And so when we subtract those two, or not subtract, but add, those cancel out. What's 760 minus 700?
760.
It's 60. And what's 120t minus 100t?
20.
How do I solve for t? And what's 60 divided by 20? So, we know that this carpenter, if he works 70 hours a week, can make 3 tables. How do we determine how many chairs he makes?
Plug it in.
Into what?
T.
T into one of the original ones, so one of the ones in orange, okay? I'm going to take the top one because it has smaller numbers. That's 10 times 3 plus 4c. What's 10 times 3? 30. Plus 4c. How do I solve for c?
-30.
Minus 30.
Divide by 4.
And then divide by 4. 70 minus 30 is? When you divide by 4, how many chairs can you make? 10. So a total of 3 tables and 10 chairs. You guys remember this, yes? Okay? So that was pretty much the book of linear models. Switching over into quadratic models, this is just the first step of it all, okay? We're going to use quadratic equations to draw different conclusions about the properties of quadratic models. Realize that I know you guys have done quadratics already before, so maybe it's just a matter of getting that refresher to help you in remembering all the properties of a quadratic equation. All right. So, first, a quadratic function is of the form f of x equals ax squared plus bx plus c, where a, b, and c are what? What does this mean? So a, b, and c are real numbers, and a does not equal 0. If a did equal 0, what would happen to that x squared? If a was 0, what would happen to that x squared? Cancel out. And then you'd just be left with this. Is this a quadratic function? It's actually a what? What kind of function is that? Which means, what type of function? Right category. It will be quadratic. So a can be anything, be a fraction, be a negative number, just can't be 0. But that's the makeup of a quadratic function, ax squared plus bx plus c. Now,
Not yet.
Wait, what?
We're good.
Okay.
Good.
alright. Now, the simplest, see how much you remember? Now, the simplest quadratic function is f of x equals
ax squared.
say it.
Oh, for real? Okay, x squared.
It is x squared. The most simplest quadratic function is x squared, aka your parent function, okay? The basis of all other quadratic functions. Now, the graph of f of x equals x squared is called a parabola. Yes. It is called a parabola. A parabola is basically a U-shaped figure. It could be pointing up like the graph is that you see over there, or it could be pointing down like so. Now, every quadratic, and including this one, the most basic one, x squared, has an axis of symmetry. Anybody know what an axis of symmetry is? Yes.
It's where the half of it, like if you were to fold it in half, it's where that vertex is, the middle.
Exactly. It's right there in the middle. If you fold it, it basically creates a line of symmetry. The axis of symmetry is basically the line of symmetry. It cuts it in half. That is what the axis of symmetry is. Now, this particular example, not every quadratic, but this particular example, it has a minimum point at 0, 0, and that point is called the vertex.
Oh, my bad.
It is called the vertex, also known as the turning point, okay? So the question ever says, what is the turning point of the parabola? You know they're talking about the vertex, okay? Now, again, it's not every quadratic is going to have a minimum. It could have a maximum if it was pointing down, aka representing the highest point it could be. In this case, it's the lowest point that's on the graph. And lastly, looking at this particular example of f of x equals x squared, the range of f of x is
Infinity. Positive. Infinity. Infinity.
it is 0 to positive infinity.
Oh, yeah.
What's around the 0? Is a bracket. Remember, brackets mean that point is included. It is a part of the range. Okay, there's not an open circle down there at the vertex. It's actually closed. And so it is included, hence the square bracket. And what goes around the infinity? A parenthesis. Infinity is not a defined number. So there's no way that you can actually close it out. It always has that parenthesis, not the bracket. A good review of the lesson from Thursday. If I wanted to write this in set notation, how would I write this? If I wanted to write it in set notation, we're talking about the range, so it actually would be what variable? Y. So you are right. It would be y is greater than or equal to 0. But what's that first part? I think you were saying. Does have a such that. Piece it together. So let me show you. Curly bracket. Yes, and it does have the curly bracket. That stands for the set of. We're talking about range, so it is the y values.
Oh my gosh, why are you calling it?
Such that y is greater than or equal to 0. That was set notation. We talked about that on Thursday's lesson when we went over domain and range. Sometimes it's a lot easier to write set notation than it is interval, and vice versa. Okay? Just remember that with set notation, you have the curly brackets, the variable to represent your domain or range. In this case, range is y, and then your vertical bar in the stipulation. Okay? So these are the basic properties of your original, most basic parent function of f of x equals x squared. Questions on this?
A good way you can remember, like, never mind, go on.
Go ahead and say it.